Hello everyone, this is part 2 of variation of parameters. Last time we saw how to prove the formula for our theorem, which is the variation of parameters. So recall that was the extra handout that was the theory of variation of parameters, and it was quite detailed proof, but kind of fun actually. I certainly enjoyed it, and I hope you did as well. So the theorem, make sure you understand the components of the theorem. The idea is that we have a non-homogeneous second-order linear differential equation, and it's non-homogeneous, of course, because it's equal to some function of x. Its complementary function, which is the solution to the homogeneous, is going to be found as normal, because actually, as we'll see, these will be constant. P and Q are going to be constant coefficients. Then, as we derived, here's what our particular solution will look like. And so, notice that it contains y1 and y2 in both of the integrals. And it also contains the function f of x and the Wronskian. And remember, the Wronskian is the solution to, I suppose this should say Wronskian of y1, y2. Okay. So that formula would be provided on an exam. Of course, I'm not going to force you to memorize it. Some people actually go through the procedure that we went through to prove the theorem rather than using the formula. But I'm going to choose to give you the formula if you're okay with that. So here's an example. And so I want to find the particular solution. And so the first thing is to form the associated homogeneous equation. And that would be, of course, just setting this equal to 0. And the characteristic equation would be r squared minus 2r minus 8 is 0. And we could factor that. R minus 4, r plus 2 is 0. So we get 2 roots. R is 4, r is negative 2. And so then our complementary function, because these are real distinct roots, would be, actually, let me come up here. Y sub c is going to be c1 e to the 4x plus c2 e to the negative 2x. So therefore what we do is we take our y sub 1 to be e to the 4x and y sub 2 to be e to the negative 2x. So in accordance with our theorem. So you can see, if you look back at the theorem, c1y1 plus c2y2. So we just chose our y1 and our y2 respectively in accordance with the theorem. Next best thing to do is to actually calculate the Wronskian. So the Wronskian W of y1 and y2 is going to be, okay, so we have e to the 4x, e to the negative 2x, and the first row, their derivatives, 4e to the 4x minus 2e to the negative 2x in the second row, and our calculation gives minus 2e to the positive 2x, because we're adding the exponents, and then minus 4e to the, again, positive 2x, which combines to give us a negative 6 e to the 2x. Okay, so there's our Wronskian. And now our particular solution. So if you want to write out the formula for the particular solution, y sub p is negative y1 integral y2 f over w with respect to x, and then plus y2 integral y1 f over w with respect to x. So I wrote the theorem out in kind of a more concise fashion without having to use the functional notation like was in the actual formal theorem. So there's just y1 integral y2 f over w. Here's y2 integral y1 f over w. So that's what we have. And basically it's just a matter of plugging in. So y sub p would be minus y1. So that's minus e to the 4x integral y2 e to the negative 2x times our function. Okay, this is our function right here. What's making it non-homogeneous is 3 e to the negative 2x all over the Wronskian, which we found to be negative 6 e to the positive 2x. And that's with respect to x, and then plus y2 e to the negative 2x times the integral of y1, that's e to the 4x, right here, f of x again, the 3 e to the negative 2x, all over the Wronskian, which was the negative 6 e to the positive 2x with respect to x. Alright, so certainly it's going to make sense to clean things up here. We've got the negative e to the 4x that's going to hang out in front. Actually, let's clean this up, clean the integral up, factor out the constant multiples here. So the 3 over the negative 6 is negative 1/2 times this negative is positive 1/2. And then we have the integral of, okay, let's see how these e's unfold. This would be e to the negative 4x divided by e to the 2x. So e to the negative 4x over e to the negative 2x simplifies by subtracting the exponents to be e to the negative 6x. Oops, and let me not forget, sorry about that. Fix this, I forgot to carry along that e to the 4x there. Okay, and then as we just said, e to the negative 4x over e to the 2x is e to the negative 6x. And then here, let's see, we get 3 over negative 6 is negative 1/2 again. So let's bring that out in front. The e to the negative 2x. And let's see what we get here. This would be e to the positive 2x over e to the positive 2x. So cancellation, e to the 0, however you want to think of it, that's just simply 1. And so now notice that the two integrals are readily integrable. And so y sub p would be the 1/2 e to the 4x times, here's our linear argument rule, 1 over negative 6. Excuse me, negative 1, yeah, negative 1/6 e to the negative 6x, and then minus 1/2 e to the negative 2x, integrating 1 with respect to x, we get x. And we don't include a constant of integration, we're just looking for the function. So now minus 1/12, okay, this was, I forgot to write the x, I'm sure I said it, and then multiplying, add the exponents, e to the negative 2x, and then minus, let's bring this x out in front. So minus 1/2 x e to the negative 2x. So there's our particular solution. One thing to note here is that you could actually solve this by the method of undetermined coefficients, because the function was an exponential function. So if you want to, for fun, you could do that. But the type of, so I'm not going to give you an example like that. Your example is going to be more like this example here, where variation of parameters is necessary because you have a function that does not have a finite number of linearly independent derivatives, such as, like I talked about in the last example, I mentioned tangent in the beginning of the discussion, but now it's cosecant squared. So this is where method of undetermined coefficients would fail, and we would definitely need variation of parameters. Okay, so we start the same way. First form, the associated homogeneous, y double prime plus y is 0. Characteristic equation, r squared plus 1 is 0. Isolate the r squared, square root, negative 1 is plus or minus I. Alright, I'm going to come up here for the complementary solution. So complex conjugate roots, e to the ax, or e to the 0x in this case, times the quantities c1 cosine bx. B is just 1, the coefficient of the I, so cosine 1x, or just cosine x. And then plus c2 sine of the same bx, so sine x. And obviously you're going to want to get rid of the e to the 0x, so just c1 cosine x plus c2 sine of x. Okay, so then the Wronskian. Well, before the Wronskian, actually, you want to consider what you should choose for y1 and y2. And so we're going to take y1 to be cosine x, and y2 to be the sine of x. Because remember, it's of the form c1 y1 plus c2 y2. Okay, now the Wronskian. So we have cosine sine, cosine x, sine of x, their derivatives, minus sine x, cosine x. Just be careful here when you do the homework. You know, there might be like a 2x in here and 2x here, so it would be minus 2 sine 2x and 2 cosine 2x. But what's going to happen all the time here is when we take the product of the diagonals, we get cosine squared minus a minus sine squared, so that would make plus sine squared of x, which is our Pythagorean identity, which is 1. Now, as I was saying, be careful. If there's like 2's in front of these, then you factor out the 2 and it would just be 2 times 1 or 2. But you'll see something very similar, I'm sure, in the homework. Okay, so now we can go to the formula. So y sub p is minus y1 integral y2 f over w with respect to x, and then plus y2 integral y1 f over w with respect to x. So at this point it's really just a matter of plugging in and then evaluating the integrals. So we have y sub p is minus y1, so minus cosine of x out in front of the integral of y2 is the sine of x times the function. So here's our function. F of x is cosecant squared x. And that's over the Wronskian of 1 with respect to x, and then plus y2 was the sine of x times the integral of y1, that was cosine of x, and then times the function again, cosecant squared x, all over the Wronskian of 1 with respect to x. Alright, at this point I'm not really going to do anything. I just wanted to show that literal substitution And I'm just going to recopy it, basically getting rid of the one that's in the denominator. So we could talk about what we need to do at this point. Okay, so I just recopied essentially. And at this point, what we have to do is consider evaluating these two integrals. And they're not really basic forms. There's some powers in there. But essentially, you'll get to a stage where ultimately, I'm not going to guarantee it, but the majority of times what you have to do is use trigonometric identities. And so, to begin with, the identity that I'm going to choose here, and a lot of times the identities that you use will just require you to change everything to sines and cosines. Like, let me see, if I write this as sine of x over 1, and then I write this as 1 over sine squared x, because the reciprocal of cosecant is sine. And then we can see you're going to get a cancellation there, so we'll do that in the next step. Let me see what happens if I change everything here to sines and cosines of cosine x over 1 times, again, 1 over sine squared x is the reciprocal identity for cosecant squared. And at that point, if we cancel the sines, just recopy minus cosine x integral, cancel one factor of sine there, we're left with 1 over sine of x. And then we have this plus sine of x in the integral of... Okay, we really can't cancel anything here, obviously. But here's a little trick. What we could do is, because we know that 1 over sine is cosecant, I'm going to choose, this is a clever little trick that you might have to employ. I'm going to choose to borrow a factor of sine and express this first factor as, instead of cosine over 1, cosine over the sine that I borrowed, and then 1 over sine x. Alright? So you might not see why I did that originally, but now you will see why I made that move. First off, though, 1 over sine is cosecant. And the reason why I made that move here was because now cosine over sine is cotangent x, and 1 over sine is cosecant x. And if I put that in the opposite order, so I'm going to recopy the first term. But then if I put this in the opposite order, instead of cotangent cosecant, cosecant x, cotangent x, now we see that that is readily integrable. It's actually one of the basic 6 because it's the derivative of cosecant, right? Negative, that is. Okay, so here we have cosecant all by itself. We're going to finish up in only it's going to take a couple more lines here. But I want to put at the bottom of the page here, remind you of the 4 special formulas that you're going to need when you go through variation of parameters. Integral of tangent of u is minus natural log absolute value cosine of u. Integral cotangent u is natural log absolute value of the sine of u. Plus our constants, of course. The integral of secant of u is the natural log absolute value secant u plus tangent u. So recall these from calculus 2. And then the integral of cosecant u is minus natural log absolute value cosecant u plus cotangent u, and then plus their constant. And so you're ultimately going to have the need and to use one of these formulas. And you can see here we've got the formula for cosecant. So finishing this up, y sub p would be negative cosine x, and cosecant integrates to be minus natural log absolute value cosecant x plus cotangent x, and then we have plus the sine of x times integrating cosecant cotangent, that's minus cosecant x, and then plus our constant. So then this gives us y sub p is positive cosine x natural log absolute value cosecant x plus cotangent x, and then minus sine of x cosecant x. Okay, I added the constant. There's no need for a constant because we're finding the function. But then you could actually go further here with this sine x cosecant x, because sine's the reciprocal of cosecant. So recopying the first term, and that would give us minus 1 because they're reciprocals. Okay, so that's basically the end of variation of parameters, but I'm going to come back and do a little part 3 quick. I want to do one of the homework problems for you, so try the homework first, and then you can come back and there's, I want to show you one homework problem kind of similar to this, and then another one that's really complicated. It's number 51 on this assignment set for variation of parameters. So that one, keep in mind, is really hard, and I'll show you the solution to that in the next video, which we're going to call Variation of Parameters Part 3. Okay, so we'll see you when you're ready.